Good afternoon. Welcome to lecture 49. So, welcome to lecture 49 on thermodynamics of materials. On the subject thermodynamic of materials. Course. Materials course. The lecture, what I said, 40, tell me, 49. 40, 49, and today date is actually 20, 20. 26, 27. No, okay. That's you are right, right? Sorry. That's right. And today is September 27, 2023. Start. So actually after little break, we are actually resuming our classes. And before I start, I take up this today's topic. Let me give you the errata. No, some errors that we committed in the previous set of videos. So that I am giving you. So first just note down this errata. Errata. This is a collection of errors in the previous classes. Video lecture 1. That's 3 or 4. Lecture 1, it is at the same time video 1. What is this? This actually close. The first is actually about closed system. If we go back to lecture 1, closed system. And here, this is I just give you. It's okay. No exchange of mass. No exchange of mass. Mass. I underline no. It was missing. So no was missing. Correct this. No was missing. This is 1 point. So this is number 1. Number 2, same lecture. Lecture 1 again and video 1. What is this? This is actually the example. Closed system example. Example of closed system. Examples of closed system. This was under discussion. Then by mistake I told that Earth is an example. Earth. But this is wrong. Earth is not a closed system. It is an open system. And that was covered in the assignment problem. But here it was wrong. So these two. Now next, third and fourth. Third is about, that is actually I have to 48. Lecture 48. Last. This is the first. This is the last. These are the errors that I could locate. Okay. Lecture 40. Oh, it is video. Tell me video 40. No. Last video so far. 40. What I said there about the problem 2. Recall this problem 2. This is let me write. It is actually recall problem 2. That's this is actual cost test problem, but I don't have to write so many things. Problem 2. What mistake I made? Delta S. I wrote minus NR ln 0.2. At this point you'll get this. This is by mistake I said. Yeah, ln V2 by V1 P2. This is this minus should be positive, should be plus. This mistake. Minus, you can very easily figure out yourself, but this is minus should be plus. So I can give you this. This is actually, so it will be finally, that is delta S will be NR ln 0.2. After substitution, this value will be minus, since it is 0.2 minus, here it will minus 126 joule per Kelvin. This is correct, okay? Fourth, again lecture 48. Lecture, hey, you can take it there. Lecture 48. See, there are many, okay, things that you can use. Video 40. Happy? Problem 3. This is about problem 2, problem 3. Right. Problem 3. First test problems. This is about again delta S. Delta S actually at one stage I think delta S2. That was delta S2. So this will actually the second step. Delta S2 was minus 12,760 divided by 1336. This I wrote actually is times my 0.26. This was missing. This was missing. Is I am giving you the result. You can see check minus 2. Right clearly. Minus 2.48 I am writing underneath. It will be minus 2.48. Okay, minus 2.48 joule per Kelvin. That's it, joule per Kelvin. So this was missing. This was missing. That's it. So have you taken down the problems? Okay. So it's a serious mistake. So this type of errors, if I tend to commit, you just okay alert me that okay, sir, this is missing, minus missing, like this. So with this, we have actually completed the errors that I have been able to figure out. So now let us take up today's topic. Today's topic is what? New topic, altogether new topic. Okay. Fugacity. Remember the second law of thermodynamics. I will continue throughout this course through last class. It is 73, 71, all second law, and at times first law application. But it is mainly second law is driving us, and whole life it is driving, whole life. So second law is actually the whole thing. I think thermodynamics is about the second law. Okay. Fugacity. You will gradually follow me. Just you keep on following, then you will activity and equilibrium. Can I remove this? I think easily remove this part. And equilibrium constant. This may be good title for our discussion. Equilibrium constant. Start with Fugacity first. So this is the topic. Okay. Today's topic. Today's topic. Start. Fugacity. So first I start with Fugacity. In this connection, Fugacity, let me write Fugacity of real gas. Sure, real gas, liquids and solids. So close. This font is okay. Real gas, liquids and solids. Okay. First I start with first start Fugacity of real gas. Fugacity of real gas. Then I will take up later liquids and solids. Okay. These are known as condensed. I already told you another name, common name together, condensed phases. Condensed phases. You give your whole attention to Fugacity of real gas. That is the whole thing. Then this will not take much time. Okay. Fugacity of real gas. I start. So start. Always you have an interconnected discussion. Always it is carrying on. Okay? You cannot avoid previous things. Based on this, today will be developed, and based on today, tomorrow. This is the whole thing about thermodynamics. Last class, first class, interconnected. The last class I will also show you delta S universe, delta S system, delta for mixing, solution thermodynamics. The same thing will come back. Start. Fugacity of real gas. So I start with, we know for a system with fixed mass and fixed composition. Fixed mass and fixed composition. Okay. dg is VdP minus SdT, which you cannot forget actually. dg is VdP minus SdT. So under isothermal condition, I recall this is general for ideal gas, for real gas, for liquid, for solid. Fixed mass means 3 moles. 3 moles ideal gas, 3 moles iron. You recall the under, I will not waste time unnecessary talks, okay? So you know this under constant temperature means isothermal condition. Under constant temperature. What it will take? dgt is VdP. Recall. This unless I have already mentioned, so unnecessarily don't subscribe. Can you box this? So important. It will be very important. dg is VdP. Okay. Now, for this here go this. For ideal gas as system, what is this? dg is what? Tell me. Here this follows. VdP is nothing but for 1 mole. 1 mole ideal gas. I will continue 1 mole, okay? And dg is RT by P dP, which is known as RT d ln P. This is known to us. This is known to us. VdP, ideal gas, easiest. Now for real gas, now for 1 mole real gas, 1 mole real gas, we got V is RT by P, V is RT by P, ideal gas equation. For ideal gas, PV is RT. V is RT by P dP, V is RT by P, 1 mole. Ideal gas equation. What is ideal gas equation of state? RT by P and dP by RT. RT is okay. Perfect. It's okay. dP by P is dln P. And dx by x is dln x. Okay. So for now 1 mole real gas, what we will do? Now for 1 mole real gas, we just write an analogous relation. This is the beginning of the complexity. Ideal gas, if it is not ideal gas, then actually Fugacity was starting to address real gas and condensed phases. So real systems rather. So now 1 mole for 1 mole real gas, we write an analogous relation. We write an analogous relation. What is that? I am writing for you. dg is RT d ln f. Analogous. Okay, we don't maintain the format. We don't disturb the format. We maintain the format, but to take care of the deviation from ideality, we consider that it is no more P, but a new function called Fugacity. So that will address. So this is, and then accordingly we will define Fugacity. The whole next we will define Fugacity. So, but basic definition is this. This is RT d. Again, two things. Please forget. Please remember. Don't forget for the whole class that 1 mole and under isothermal condition. Remember this is. Don't forget 1 mole. So molar property will be very important here. So note for 1 mole, and I am this point, and for isothermal, for constant isothermal condition, for isothermal condition. These 2 points you don't forget that we are considering. You just again give a, this is a starting equation for fugacity, where F is a property, F is fugacity of the gas. Fugacity of the gas. Okay? You can turn this on also, no problem. Huh? You can turn this on also. You can use this also if necessary. This fan. Okay, feeling is okay. It's okay. Okay, very good. Okay, so this is so box. Okay, now fugacity. Okay, now we try to explain further or analyze further the F. What I start with. Remember, so right here, it is better. So from 1 perhaps 1, 2. Don't forget. Acha. So from 1 and 2. Can I write this? Tell me. Acha. I'll be careful about the font. RTDLNF. Are you all set? Take a look. This addresses which system? This is for real. This is for this is all isothermal. Isothermal one mole. This is also any system, means real system. So both for real systems, so I can equate them. Okay. Now at this point, I actually introduce a term V. At this point, what is V? Actually, I tell you. We consider the equation of state for a real gas. Consider the following equation of state for the real gas. For the real gas under study, for the real gas. What equation I am following? You follow easily. V is RT by P. This is for ideal gas, but we consider since there is a deviation alpha. Alpha is actually gives the measure of deviation, or actually gives the is function of deviation. Okay, RT by P minus alpha. This is the equation of state for the real gas, where alpha, which measures the which actually quantifies, which is a measure of deviation from ideality, which is a measure of the deviation from ideality. Note this, alpha identity. Alpha is function of temperature. Alpha is function of temperature, and alpha is not function of pressure. Particularly, is not function at low pressures. But will be function of at high pressure. But will be function of pressure at high pressure of the system. High pressure of the real gas, high pressures. Acha, at low pressures. Okay. So we consider this for alpha is not function of at low pressures, and also note at low pressures deviation from ideality. Deviation from ideality. Deviation of the gas. Deviation of the real gas from ideality. Deviation of the real gas from ideality. Ideality is small. At high pressure, deviation large. Low pressure, and at tending to very small pressure, when pressure tends to 0, real gas behaves ideally. real gas behaves ideally. Okay, so this is actually I consider, or also, or V is what? Equation of state is RT by. So I consider so small deviation from ideality. Deviation we consider, otherwise we don't study fugacity. Fugacity means deviation from ideality. So V is RT by P minus alpha dP is RT dln f, or tell me RT dln f by P is minus alpha dP. Will you agree with me? I hope you will agree with me. Take a look. Side change. Side change. dP by P is what? dln P. The dln go to the other side and to this side and side change and alpha dP. Okay. Or ln f by P is minus alpha by RT dP. Happy? Okay, good boy. Alpha by RT dP. So you can remove this if necessary. If it blocks your side, it's okay. Alpha by P. D, Paratna, there is a D. I missed this. D, here I missed D and F by P. Okay. Now I'm integrating this. Integrate from P tends to 0 when the gases, real gas tends to behave ideally, to P is the pressure under study, P is P, and corresponding F by P, the variable on the left hand side, when P tends to 0, it tends to behave ideally, and F is same as fugacity same as pressure itself. Okay, F by P, F and P has no difference. Okay, when what it will be RT dln, where it is VDP here, right? RT dln P, RT dln F. So F will be P if it is ideal behavior. So P tends to 0, ideal behavior. So F by P tends to 1, and F by P here, F by P is upper limit. F by P is F by P is F by P. So F by P tends to 1. Or quick integration, ln F by P minus ln 1 is minus alpha by RT dP. I am taking one thing here, alpha, okay, alpha by minus alpha by RT outside. Outside, shall I show you this? Alpha you take outside the integration, and T will also go outside. You understand why T go outside? Constant temperature. It is effect. So temperature and R is a constant. So alpha takes, I take this I have to explain. Explanation is due why alpha is also taken outside, and then it is integration of dP. P tends to 0 to P is P. Note for small deviations, follow me, please follow. What I have said, alpha is what? Alpha dP. Alpha is not function of pressure, function of temperature. Alpha is very major. At low pressure means small deviation. I am considering for small deviation at a low pressure regime, low to medium, not very high pressure. So for small deviation is there. Small deviation, then for general I will consider later. For small deviation, if you allow me to consider small deviation of the real gas is small, under small. Okay. For small deviation, we have already noted alpha is not function of pressure. This I will also establish later. I'll show you why alpha is not function of pressure, but always function of temperature. So for small deviations, note why is not function of pressure already noted, and we are utilizing this. That's why it is outside. Okay. So what you are getting, tell me nicely, ln sir F by P is nothing but alpha P by RT. Are you satisfied? I think it's easy, very easy. Integration is okay. Or F by P, or F by P, right? Continue here. Or F by, don't have to come because I will remove this top. Okay. Or F by P is e to the power minus alpha P by RT. Yeah, it is a minus. Now e to the power minus x, what is the series? Recall e to the power minus x series is 1 minus x plus x square by e to the x square by factorial to a nature. What happens to minus x cube by factorial 3 etc. So for small x, e to the power minus x is considered as 1 minus x, and alpha p by rt is actually small deviation. For small deviation, alpha by p note right. So it is equals to, I am writing e to the power minus x 1 minus x 1 minus alpha p by rt, right? For small deviations, since small deviations means small pressure range. For small deviations, actually, truly speaking, alpha p by rt is the deviation measure, but alpha is also function of alpha p by rt. So for small deviation, alpha p by rt is small. So I am entitled to make this approximation. Since is what? What are they? Is small. Is if it is small, then this exponential expansion will work 1 minus alpha p by rt. Acha, very good. Or what you will get this from this? Okay. A by p. Please do this. 1 minus p by rt. What is your alpha? Please tell me. Alpha. Go back. Beginning of the alpha here. What is alpha? Tell me. Rt by p. Right nicely. Minus v. Rt by p minus v. So what it is? Can I write here? Can I continue here? Okay. Let me complete here. Is 1 minus 1 plus pb by rt. Are you happy? Are you happy? So this is nothing but pb by rt. I will go with this, go up with this one. Shall I? I'm just removing this. No, only. So only one thing I write here, which will be used right here. dg, this is saved. dg is vdp, that I have removed this one. And what I will remove here, v is rt by these are the important considerations. Again box, this two, third is what? What is what I said? V is rt by p minus alpha. Dg is rt. I have removed this. Right there. dg is rt here. Box, another box. rt d ln f. rt. See there. This I saved here. Then I remove everything. Then I can remove everything because I will not need other things. These three things actually I have saved. Can I remove? This. Remove this. So what I get? F by p. So start. Can you give a star here? Star here. So I rewrite it rather. F by p is what? Pb by rt. Is what, sir? P by rt by v. P by rt by v. Can you recognize what is rt by v? P is the pressure of the system talking. RT by V is what? Ideal. P ideal. If it were ideal, RT by V would be, so it is not P, but it is P ideal. This is our final relation. Okay, F by P, that is, write nicely. F by P is P by P ideal. And box this by all means. Box this. This is your relation. Okay. P ideal. Why P ideal? Can you Nirjor? Why it is P ideal? NRT, P ideal NRT by V. Throughout 1 mole and constant temperature, then you have no problem. Or what you write? P is square root F times P ideal. So we say, what we say? Fugacity, pressure is the geometric mean. Pressure is the geometric mean of fugacity and P ideal. I mean, fugacity is such a function for small deviations, of course, given. So we can say, we say pressure is the geometric mean of F and P ideal. So fugacity is such a function. So this is actually you can say. You will say two things. Anytime you are asked what is fugacity, the name is a very unusual name, fugacity. Okay, pressure fugacity. You have to say what is fugacity. Then you can say, sir, origin. If you go always to the origin. And sir, this is such a function that dg, the change in the free energy, is RT d ln f under isothermal condition, sir. For real systems, fugacity refers to real system. Ideal system pressure and ideal pressure all are same, one thing. So this is okay, very good. So we say pressure is the geometric mean of F and P ideal. Very good, very good. So this is for small pressure range or small deviation. This much is okay. This will actually will serve our purposes for small pressure ranges. Okay. What else? This is fine. Very good, very good. Now actually let us continue discussion on next thing. Another way of what anything I have to say this? Okay. So I tell you one thing. I'll give you two ways to define fugacity so far. You will be asked this question obviously. What is fugacity? Just you have to say there's such a function that change in free energy of the system dg is RT d ln f under isothermal condition. Suppose in nitrogen, sir, or say carbon dioxide, sir, dg carbon dioxide is RT d ln f of carbon dioxide. This is actually the meaning of this under isothermal condition. One mole of that. These two you say basic, and another is this like this geometric mean. Pressure is the fugacity is not the geometric mean. Pressure is the geometric mean. Fugacity is such a function. Okay, I tell you three things you note. Three things you note. Three things you note here. You already noted, I hope. One is the pressure. Pressure I will explain. P ideal, and still another fugacity. Fugacity has what unit? Obviously the same unit as pressure, atmosphere or others. P is what? The pressure in this room. What is the applied to this air in this room? What is the pressure, sir? I will measure pressure, sir. This is real gas. So measure by the barometer. If it is temperature thermometer, barometer. So that is the measure this. P ideal is, sir, I am coming to this. P ideal is what, sir? If this gas, P ideal I will go by this V by RT or okay, nRT, okay, number of moles. Suppose it is from 0 you started, you pack certain number of moles, you know. So this is N, you know, temperature of, you have to know. The P ideal is follows this PV by RT, is nRT. So that is ideal value. This go by equation. This is in measure. Go by the equation, only you know volume and temperature, number of moles. F is what? F is a from this. F is such that pressure will be geometric mean of this, and that is also what kind of pressure. Okay, so real system, these three terms. Okay. Now start. Now another way, next important, next. Another way of what you call this? Another way of whatever. Okay, of another way of representing. Another way of representing the real gas behavior and its deviation from ideality. Deviation from ideality is what? Is the property of compressibility. Is the property of compressibility. The symbol Z. With this, actually, we have a long. Should I suggest you open this and turn on this mosquito? Okay, it will be better. Or if this is okay. This is okay, though. Oh, great. Compressibility. With this will be. Okay, Z. What is Z? I tell you. Z is given as PV by RT. Z is defined as Acha. I write here, although you have understood, not bad. Note unit of fugacity is what? Is unit of pressure. That is atmosphere. Please. Okay. So clear. Clarify everything. So Z is PV by RT. The compressibility is PV by RT. Okay. Now you will so relate here. Relate Z. Please follow. Z is PV by RT. What is the value of Z? PV by RT is well known 1. But that is for ideal gas. So it is either greater than 1 or less than, typically less than 1. More like, but it can be greater than 1. So that is the consideration. So it is a measure of deviation. Whether Z is greater than 1 or less than 1 deviation. That measures the deviation from ideal gas behavior. So whether Z, how, so relation now, alpha is a measure of deviation. So relation between Z and alpha. Quickly, do this quickly. Relation between Z, one way of measuring deviation, another way is alpha. What is, tell me, what is this? B is, right, this way, quickly, easy thing is very quickly, do this, quickly. B is active by P minus alpha here, I have noted for you. or I'm writing here itself. Z is P by RT. P by RT, as you know, as defined as. I've written. Z is defined as. Is what it is? Tell me. P by RT. P minus Z is P by P by RT multiplied by Z is P by RT is B is this much. So P by RT times this. So 1 minus alpha P by RT. Will you put a box here? Important equation. This is a connection between alpha and Z. Anytime you have to move from this to that. So I have connected you. Alpha I have given you, but Z, in terms of Z is this. So I am talking of Z, okay, for a while. Then I will take up more things, okay. About Z, I will give you a scale, then you will be more interested to this. Acha, this I will tell you, okay. The Virial, let me complete Z. Then I will take up the further fugacity and fugacity values based on Z. The Virial equation of state, they say, or equation of state simply, Virial equation of state for real gas is what? I tell you, as a function of pressure. Z is, follow me, is 1 plus BP plus Cp square and dpq infinite series maybe, okay, goes on. These are B and C are called, this B, C are called virial coefficients. They are function of temperature, but don't worry at this point, you consider these values. Okay, Z is, you have understood, Z is 1 ideal plus deviations coming, this be positive, negative, etc. Next I will show you, then I will take up this. This is an important discussion coming. Follow me. This nothing like this to understand, and you will. This figure is very important. Z I am plotting. Z is what? PV by, as you know, defined as PV by RT against pressure I am plotting. If I plot against pressure, this is the value of 1. Put a dotted line, may be helpful. This is for which gas? Good boy. This is for ideal gas. Now real gas I am drawing for you. I am drawing for you. This is greater than 1, right? This side is greater than 1 and this side is less than 1. This side is less than. I am drawing for some curves. Ideal gas, okay. I give you, this is say 0 atmosphere. This diagram I will draw, okay. Barrier here. So let me draw first time. Then I should not forget. T is for right on the top. T is what? 273 Kelvin. I am drawing this plot. How Z is changing with pressure? Z is a function of pressure. Z is changing P. Okay, when P tends to small, let me draw. Let me draw. Achha, this is actually, I'm sorry though, but anyway, since I've already known, atmosphere. What value? 200. This is 0, 200 here, 100 atmosphere. This may be 300. Just taken from gas scale actually. This actually gas scale. This is for say which gas? Methane or ammonia rather. Because I have drawn this way, ammonia. Then methane will be, this is methane, methane gas. Nitrogen will be similarly, but deviation is less, and will show a crossover. This is nitrogen. This figure less and crossover. This is nitrogen. And most important is, I'm very sorry, thanks. This is nitrogen gas, methane gas, ammonia gas, and this is what? This is very important, hydrogen gas. Z greater than 1, Z. Okay. So this is the picture, compressibility. Now, I tell you what, this is okay, this is the picture. As a function of pressure, 300 and this goes on. So 400 and goes on. Z versus P. This is the equation, this has been given. Acha. This is okay. Now I tell you the rationale behind the consideration of Z is P by RT. This is easy though. Compressibility. Remember what is compressibility? Is not how easily it is compressed, how difficult it is compressed. It is to compress. That is compressibility. No, it is like your what is that called? Modulus of elasticity. No, modulus of elasticity. You remember how difficult to it is actually stretch. Okay, high means steep. Low means it is easy. So low value, but it is rubber. It is easy. So like this. So Z is compressibility of the gas. What is this? Very easy. You consider please this. Pressure by RT by V. I'm very sorry. Better is V in terms of I can pressure also, but anyway, this will you have distinct advantage here. I'll show you sketch. V by RT by P. What is this? V sir. RT by P is again V ideal. V ideal. 1 mole, sir. 1 mole. I will not talking in moles. V ideal. So what does it mean? What is? Shall I? Is okay. Ideal. V ideal. This you can write. Z is. I show you with the figure. You have taken a gas here. Why it is PV by RT? You will easily follow. Sir, you have taken a gas. Please. This is okay. Under what temperature? T, sir. This is under what pressure, sir? Certain pressure P. Ideal gas. This is the volume. Say B ideal. No problem. 1 mole. 1 mole. Shall I write? You have no difficulty because PV is RT, satisfying PV is RT. This is V ideal. Now, if it is real gas, nitrogen. Follow me. Nitrogen, if we see under the same condition, same pressure, 5 atmosphere, 3 atmosphere, same temperature, 500 Kelvin, 200, 300 Kelvin. A nitrogen, if it were, you have, let me draw. This is V real, V nitrogen. Okay, V real, that is V real gas. Less volume. Can you expect? What is the origin of real gas and ideal gas? We know where. Fundamental. What is ideal gas? No attraction. Real gas, there is attraction. Attraction, the moment at the same pressure, they are coming closer. And volume results is less. And if it is hydrogen, let me draw at the same time. This is again V This is the hydrogen, sir. Volume hydrogen again real. Real. This is also real. Real though. Why it is greater, sir? Greater than ideal. The ideal. Greater than, because hydrogen is tiny gas, tiny molecules. They are not so active. They repel as they come to. There is a tendency of repelling. So that's why they take repel, so greater volume. So from this you can yourself conclude what is Z. Now tell me. So conclude inference quickly for three categories. Three categories all along. Yeah, does it hurt you? It's okay. You can turn that on. You let it start. Yeah. Good night. Okay. Okay. It's okay though. There's not much time left. Okay. So slow. Three things we have. One is ideal gas. Another is real gas. Two categories of real gas. One is hydrogen category. Another is nitrogen and others category. These are real gas. These are hydrogen. Hydrogen exceptional. So you write quickly. For ideal gas, I am summarizing. It helps you. For ideal gas, Z is 1. Sorry, Z is 1. For real gas, for hydrogen, sorry, nitrogen, real gas. That is better. I write real gas. For example, nitrogen. Right? It is better. For real gas, e.g. nitrogen, Z is, what is your comment? Tell me. See here, is it nitrogen? Less than 1. And you see, shows less than 1. Also less than 1. So Z less than 1. And for real gas, again real gas. For real gas, namely, e.g. hydrogen, maybe helium also. But I am talking of hydrogen. Z is greater than 1. Please complete this table. But at the same time, very good. Achha, this I will actually tell you. What shall I tell you? Fugacity is greater than pressure. F by P is P by ideal. You will get this later on. Achha, so far, inference, save this inference, and you have already understood this, no problem. Okay. Now, what else I want? Nothing else. Now, I will give the relation between Z and Fugacity. I will return to Fugacity now. Okay. See, I have not discussed it from here. If you follow this, after I have completed this, I have not talked about Fugacity. Okay, but Fugacity, deviation from ideality, alpha, Z, all are actually same thing. They are talking of the same thing, the deviation. And this topic is the real gas means deviation from ideality. And liquid solids I will discuss later. Okay, that is not difficult. Shall I here or anything else? Right? Let me jot down here. F by P is P by P ideal. This is important lessons I am right here. What is this? This I am writing. Z is, please follow this. Box, the one that I have boxed only. Save this side. Anything? Z is or nothing else. Nothing is. Z is a function of, that also write that. That is important. Virial equation of state, what? Tell me. Z is 1 plus Bp plus Cp square plus dpq, etc. Not this actually, nothing else. So you just make some room. I'm sorry that I have removed the gas, this one. But anyway, continue. Quickly, it will finish. Okay. Now start again. Again consider what? The previous lesson. Achha, what is the topic? Now connect Fugacity and which is F and Z, compressibility. Okay, Fugacity and F. Okay, very good. Okay, what is this? Z. Start with what is the starting point? B is I am very sorry. Start again. I am writing two fundamental things. I have now removed. Yeah, only this side. The box for small pressure. Box. Virial equation of state. This is okay. So quickly, what is it? Fugacity. Please. What is this? Start. Recall. dgt is VDP is like last time, Just with some of the lines are exact repetition. Is what V is what VDP is what tell me RT DLNF. You see here still standing. This I what to get the relation between fugacity and pressure. That this one to derive. So I'm writing this. That is writing tidy up. Writing left hand side RT DLNF is VDP. Please write now. Right. V is what? V is RT.
Can you please write L? L. L is RT DLN.
DLN. Oh, thank you so much. Thank you. Very good. This type of mistake I make when I under pressure of time. BDP. This here accepted. What is B? By the way, RT by P minus alpha. Okay. Okay. What is V is equal to RT by P minus alpha. The dp. Thank you. Or again, same steps I'm writing. You follow same steps. Or RT. So I will not repeat. Only give the result. RT D. Oh, this is a chronicle habit. RT DLN F by P. Till then is tell me yes. You actually Devopam will tell us. RT DLN F by P. Take a look. Is what? No, take a look. RT, don't hurry. RT DLN F by P from this to this is what? Is minus alpha dp. Oh, dp by P. I'm taking left hand side. Is okay to? Minus alpha dp. Or DLN F by P is minus alpha by RT dp. Any trouble? Sugallan, take a look. Where? These are saved here. These are saved. Piece must piece composition. Again, second step. At BDP at the left hand side. Okay. Well, sometimes I write actually, left hand side. Okay, okay though. Okay. Now what is this alpha by RT? This. Use this link with Z and alpha. Yeah. What is this? What is alpha by RT? Will you please tell me? I'm writing from this. Please minus alpha by RT from this. What is minus alpha by RT? Right. Minus is Z minus 1. I'm going to Z. The link between Z and alpha. Minus alpha by RT, Z minus 1 by P. Is correct? Please check. Minus alpha by RT is dp by P. Is happy though? Okay. Take a look. Alpha minus alpha by RT is correct. Is Z minus 1 by P. Or dp by P. What is this? Z minus 1 DLNP, right? This. Now again the integration. Z minus 1. No, don't worry, don't mind. Just keep it. Don't last line. You don't. Or integrating. I'm integrating. So I'm writing here itself and here itself. What is the integration? Convenient integration limits. One limit is real gas nature, ideal gas, real gas. Okay. So that is the convenient limits. What is that? P tends to 0. Actually, I will use P is 0, but tends to 0 is better. And P is P. P is P. And what is the corresponding here? So, what is the here? Lower limit is F by P tends to 1, by 1, okay? Tends to, or 1 you can write, is 1, F by P is F by P. Quickly, it will not take much time. Let us go a little faster. Or ln F by P. Again, like before, ln1 I am writing for you so that you don't have difficulty. Is what? Write this 0 to P Z minus 1 dp by P. Happy? No problem. Font is okay, more or less. Now it's okay. Font. Little bigger? Yes. Still bigger, right? Little bigger. It's okay. I'll be careful. Is what? Right? Again, write. Or leads to, I'm writing this side. Or it will save also. To save ln F by P. This is 0. Is nothing but this is your famous relation. Fugacity in terms of compressibility, sir. P is 0 to P is P. And will you box this by all means? Okay, this is This gives you in terms of fugacity, pressure difference, in terms of compressibility. Acha, one thing I forgot to tell you. I'll tell you. Acha, I'll take up this from this point. Ln left by 2. Acha, shall I complete? Acha, if I forget in time, you'll say, sir, you'll say something. You don't tell. Yeah, I'll remember this. This I will remember. Some comment about this one. Already finished, but I forgotten to make this comment that I will take up later. But not difficult. But let us continue. This is actually, we have got some this. This is the relation. Now you see, now for small deviation, what is Z equation? See, 1 plus Bp plus Cp square, you consider two term only. P square you just is 1 plus Bp. The coefficient, Virial equation you have considered. Substitute back. So case 1. Case 1. Now, application. This application of this. Application of this. Case 1. For small deviation. Z is for which Z is 1 plus Bp apply. Z is 1 plus Bp apply. Okay, so what is this? Quickly. ln f by p. Write whatever you can write. Integration. Tell me. Z minus 1. Shall I write? Sir, I should not write. No? Can I save time? This 1 plus Bp minus 1 means Bp. Bp, I am writing Bp of course, by P, dP. P is 0 to P is P. Happy, sir? Or, sorry, ln f by P is what? Tell me, Pp cancel, Bp back. B is a coefficient, B will be outside. Constant, okay? Function of temperature, but temperature. So don't worry. So B will be outside. Bp, sir. What is Bp, sir? Again back for the equation Z minus 1. So you get a fantastic relation, fugacity in terms of compressibility. In terms of compressibility, F by P is okay. P is P. Okay. In terms of alpha, if you ask me, you already got this. What you got? Can you check back? Sir, in terms of alpha, F by P is e to the power minus. F by P is after integration. F by P is e to the power minus alpha P by RT. Take a look. When I expanded the series, F by P is F by P is e to the power minus alpha P by RT. After third or fourth step, fifth step maybe. F by P. So F by P as a function of alpha. You got this? E to the power minus alpha. I'm sorry, e to the power minus alpha. This is the relation, and then we expanded on that. So this is okay for small deviations. You consider this. Okay. So here also get this in terms of alpha Z. You want to know by all everywhere possible. So no. Okay, nothing is actually kept away, kept out. Okay. Ln by. So this is actually very good. Will you? Acha, I'll take this. Case 2. Okay. What it shows you? What is so? Acha, I'll take up that one quickly. Case 2. Complete. Let me complete this. Case 2 one by one. Certain cases only. Okay. Main thing is over. So case 2 is what? For large deviation. For large deviation. What is this? Ln f by p. Again, write this same way. What is this? Write this equation. Fundamental equation. Right. Integration. Z minus 1 dp by p. P is 0 to P is P. Happy? Quickly. Is what? This time tell me. I am writing. P is 0 to P is P. What is Z minus 1? Will you please tell me? Take a look. Now we will not consider the other term. Third term, you consider include that one. Cp square. So what is this? Z minus 1 Bp plus Cp square. Please, Bp plus Cp square by P. dP. Further you do this. If you do this integration, Bp, I'm doing it, you follow, understand? Pp cancel Bp and then Cp, half Cp square. It's okay though. Thank you so much. Half Cp square, will you? Take a look. Pp can Cp, half Cp square. So, but in any case, Bp plus half Cp square is not Z minus 1. Even though I started Z is B, right? Consider here, I can write this here. I will use this. Z is another term, Bp plus Cp square. Just for demonstration purpose. Then, but is it Z minus 1? Note this. It was Z minus 1. But this time it is not Z minus 1 because Cp square. is half CP square. So good. These are the observations you have got this. Quickly another comment follow from this. You follow another comments, other comments. Then I'll tell you something very interesting stage we are about to finish. Other comments quickly, quickly. Other comments ki. Yep. You know one thing is this. Acha. Alpha. What is alpha, Baba? Well, alpha. I said start from alpha. Alpha is what? Z and alpha. This will be useful. What is Z is 1 minus. Acha, right. This. Other comments. Alpha versus P. Alpha as a function of pressure temperature. This is the topic. Alpha as a function of pressure temperature. This is the topic. I said what I said. Recall? Do you recall what I said at the beginning? Alpha is what property? Is such a property that it is always function of temperature, sir. But function of pressure, high pressure, but not at low pressure. Let us. I'll demonstrate this now. Whatever I have said, I'll demonstrate. You demonstrate how you know Z relations. You say. Please start with this. B is RT. B is start with this. Best start with this. Why? Why? It is already there. Z is, start with this. Z is 1 minus alpha P by RT. Now use this. When for small deviation, this is another set of comments. Okay, one set of comments already I have got you. What you, I tell you what. Suppose I give, what is the application of this system? Compressibility of the gas I have given you. Can you find the fugacity at a pressure? Pressure I am giving. What is the fugacity? What is the fugacity, sir? Value give out. You are talking many things, equation. Value of fugacity. That 30 atmosphere. 40 atmosphere. Okay. This is the. I shall give you this type of relation. Okay. This relation. Okay. So at a pressure, say this relation. This is relation. So for small thought, I consider this relation. 1 plus BP. So what is the 1 plus say? 0.3p. 1 plus 0.3p. Apply here. 1 plus 0.3p minus 1 0.3p p, and I will give you pressure. When I ask a question, I should give you that at this pressure what is the fugacity. At say since low pressure regime, so I consider 50 atmosphere. The 0.3 what I have said 0.3p, 0.3 times 50 is f by p, or ln f by p. Then from this you will get the again f by p. So p is 0.3, so ln x. You will do that. So you will get the fugacity. This one or two problems I will actually solve you. Okay, happy to. Z is 1 minus alpha p by RT. This is so similarly here you must know this. Similarly, so Z is 1 minus alpha p by RT. Or tell me what is Z? Apply. The case 1. Case 1. What is the case? You know, two cases. Small deviation. Small deviation. What is Z? Please tell me. Tell me. 1 plus 2 term. 1 plus BP. Means linear relation. Z is 1 plus BP. If you take a look at that one, achha, can I remove this? This will be helpful. This I am very sorry that I had to remove that, but I will return that figure. No, so important figure Z, which is PV by RT, is against pressure. Quickly. This is Z is 1. This is greater than 1. This is less than 1. Not negative. Okay. This is ideal gas. The nitrogen. Like this. This is a methane. Okay. Methane. Nitrogen. This will suffice. Okay. Hydrogen. Contrasting. Hydrogen. Etc. This is qualitative drawing. Okay. For small deviation, have you noted this? Small deviation. This is kind of straight line, linear behavior. Z versus P. P is what? 0 atmosphere. Temperature, right? Also 273 Kelvin. P 1 atmosphere. This is your 200. Okay. Please see here. Take a look here. This is about linear for small. Then gradually it becomes non-linear and curves and etc. Complicated. Okay. Here some linear. So for small, say 5 atmosphere. This. So your linear relation. Also see for small deviation, what is the relation? See, take a look. Z is what? 1 plus BP. See, 1 plus BP is what type of relation? Linear relation. Z as a function of pressure is a linear relation. So this is actually Z is 1 plus BP. Can I write here somewhere? Z is 1 plus BP. Like linear relation. Can note here. Linear relation between Z and P. Z and P. This is nonlinear relation, okay? This is a nonlinear relation, okay? Don't tell me. 1 plus BP, quickly. 1 minus alpha P by RT. Happy? 1 cancel. What is alpha? Tell me. Alpha is, tell me, you can do yourself. PP cancel. PP cancel. Minus BRT. What is your comment on this? Alpha is minus BRT. What is the comment? Alpha is a function of temperature. For small, no pressure term has actually cancelled out. So alpha, this shows alpha is function of temperature, is not function of pressure. As you actually, so I tell you, link up. That's case 2. Link up what? You link this small deviation, what you are getting, that alpha is not, this is demonstrated now, okay? And what you get this, what is what small deviation, what you tell me some quick actually answer, okay? What is this? Okay, quick, okay, what's quick response, okay? What is this about low pressure, small deviation, what you get? Sir, F by P is P by idea, is okay. What is this? Z is 1 plus BP. Linear relation, this you said, okay? And what you said here, alpha is minus BRT, okay? And what is alpha Z relation? Always, forever, Z is 1 minus alpha P by RT, okay? That is general, that is not a, okay, pressure. Case 2, large deviation. What is this? Please tell me. 1 plus BP plus Cp square, please, minus alpha P by RT. I'll write here, you check with me. What is this? 1 minus alpha P by RT. Sorry. 1 minus alpha P by RT. I want to finish this part here. Or 1 cancel. What do you get alpha as? Tell me. First term is minus BRT as before, perhaps. BRT, then another term will now see, okay? So PP cancels, CPRT. Please check. I'm writing, but you should check. Will you check? And give a box. Give a box here, give a box. Take a look. Do you see this? Please check this. It's okay, I will not go get actually lower anymore, okay? Minus BRT, what does it mean? Function of temperature and pressure, what I said, okay? So this shows alpha is a function of both temperature. Shall I? I'm not, this part is over, okay? This is one thing I said, I'll tell you. Now, before I remove this, I'm telling you something, please follow me. Now some. Oh, good boy. Okay. I was so concerned about. Thank you so much. Thank you. Very good. That's great. See, minus. But does not mean it's a function of pressure and temperature. Okay, happy. So quickly I'll tell you. You follow me. Acha, thing. Ideal gas. See, again contrasting 3 things. Ideal gas, real gas 1, real gas 2. Means nitrogen, hydrogen are the 2. Okay. Two opposite ends. Okay, ideal gas. What is this? You know, your comment you tell me first of all. You say Z is 1. Good boy. And what you got this? Z is 1. And F is, if Z is 1, what is this? F. Z is 1. This is what? F is. Will you write this from this? Okay. Yeah. Tell me. Z is 1. What is the F by P is what here? Is actually F is P, right? Actually, F is P, it is very easy to say. Z is 1 means ideal gas. For ideal gas, there is no fugacity. Means, yeah, if there is fugacity, that is same as the pressure. And pressure is same as the ideal pressure. 3 things. Fugacity, pressure, ideal pressure. 3 things. That's all same, sir, for ideal gas. Pressure is ideal pressure. And fugacity and pressure has no difference. One equation, sir, dg is RT, dl and P. So please, Z is 1, F is P. You have got this. And note here, you will write another one here. That is, acha. Right, I'll Joule-Thompson cooling. No Joule-Thompson cooling. Please note this because I want to complete this part. Please mention this part. I will explain this. Maybe may not be today. Joule-Thompson, very important. Thompson cooling. No Joule-Thompson cooling. Joule-Thompson effect they say. But cooling, typically cooling, it can heating also. No Joule-Thompson cooling. Joule-Thompson cooling or no Joule-Thompson. Okay? Okay. Effect. Effect, right? Effect. Because cooling I will use later. Effect. Again, consider. What is real gas 1? Real gas. What is the name of this gas? Nitrogen. What is Z is, tell me? Z is less than 1. Less than 1. What is your con follow? Fugacity is not pressure, but it is not enough. Is not equal to, but whether greater or less. Answer now. And yeah, Z less than 1 with this is a simple thing. Then we get an idea. Here this is a more complicated, but very easy here. What is it? Less than 1 is F less than P. Fugacity will be less than pressure. That you will see. Pressure is the geometric mean, but I can show you later. F less than pressure. What I write? Joule-Thompson, JT, Joule-Thompson. Sorry. Joule-Thompson. We say cooling. Joule-Thompson cooling occurs. Very important. We use this. Okay, in many industrial applications. Okay, many. Okay, Joule-Thompson cooling. And real gas. Next, another real gas. Hydrogen. Opposite behavior. Z is greater than 1. What is your comment? F greater than P. Joule-Thompson, right? Heating. So this time no cooling, rather heating. But I can tell you that there is actually what is they call inversion point temperature, where cooling becomes heating becomes that, don't worry. But so far this is actually room temperature or ordinary pressure, ordinary temperature. This is the answer. So this part you have got this, okay. And if I ask you this, okay, if you follow this, another curve, if I may draw this, F by P, will it be okay? F by P is what? Then on. So don't worry. If necessary, I will call this. This part is over. Okay. So 1, 2, 3, 4. So all over. L5 function. Last is draw a line there. One thing I missed actually. One thing I missed that I said, I wrote here. One comment I missed. Comment from F by P is P by P ideal. Missed out. You will note this. What does it mean? Follow this. What is this? When okay. Geometric mean is already given. Okay. Percentage errors. Suppose you say, I don't consider Fugacity as pressure. Only one thing. So, but there will be error committed. So percentage errors in considering F as P. F as P. Not allowed. Different. They are different. F as P is the percentage error in considering P as P ideal. Considering P as P ideal. See this point. This is the F by P is P by ideal. So you consider this actually same, then make it the same. That means for ideal gas. Now, hence for ideal gas, always reconcept. So hence for ideal gas, what is your comment? Hence for ideal gas, DG is RT, DL, and P, and RT, DL, and F. These are all same. F is P. Tell me. That's right. This is for ideal gas. Okay. So this is kind of over. Okay. This part, our discussion, that depends on time. Actually, little bit left out. And do you want to stop today, or can I continue a little bit? This is totally up to what time? How long? It is 7:30, na? 7:30. Acha, Joule-Thompson effect. Let me complete the F by P is P by ideal. Then actually this ideal gas behavior will be completed. Then this is better. It is better actually. So many things I have said. Only okay. Allow me 10 minutes maybe. 10 minutes you have to give. It is very important. Okay. Important study or say Joule-Thompson effect. Shall I? Can I have given you okay Joule-Thompson cooling. Okay, but shall I? Remove this. Make some room. Interesting. So all remove this. Only you can retain these ones. Okay. Even remove this. quickly. Joule-Thompson effect and what is the fugacity. Okay, before I complete this. Another, last, I said 3 ways. Someone will suddenly ask what is fugacity. They will not say anything, any word further. What is fugacity? Or what is the fugacity? What is fugacity? One answer, such a function, origin, this is the original. Another function is for low, the small deviation, for low to moderate pressure also. So these two, pressure and ideal pressure. What are the three you have on? One is experimentally measured barometer, another is idealized value PV is 30, another is the I don't know, so I will get this from this geometric mean property. That is the fugacity. And this is second, third is coming. Follow. What is question? I finish this, then Joule-Thompson effect. What is the significance? Significance, or what is the significance? What do you mean? What is the significance of the statement? What is the significance of the statement? Fugacity, what is it? Fugacity of nitrogen is 95 atmosphere when the real pressure is, guess, when the real pressure is, tell me, 100 atmosphere. Is correct? I think the question is correct, at least you judge this. Why it is correct?
Yes.
Less, must be less. If the question is correct, it will be less than that, less than. But what is the significance of this answer? This answer. In origin is this, remember. Free energy. Fundamental properties there. So this answer. In short, it means free energy 1 molar. Always molar I am discussing, I told you. Free energy of 100 atmosphere real nitrogen, real gas though, is actually nitrogen gas. Nitrogen is free energy of 95 atmosphere idealized, which is ideal nitrogen. If you understand this, actually very good. Same, this is the meaning. If fugacity is 95 for 100, the 100 atmosphere at 100, so at a given temperature I am not mentioned, it is implied, certain temperature, there is a free energy. If it were ideal, then 95 atmosphere would give the same free energy, would result the same free energy. This is the meaning of this. Free energy, because origin is this, relation. And there is a standard, a little, okay, lengthy, but I will not take up this. This you always understand. This, okay. The fugacity of this means, what is this is the real gas, which you are studying. And this is the question, for whose fugacity is 95 atmosphere at the pressure of 100 square. Okay, good. This over. This part is over. Now take up. This you remember. This is actually one smart way of answering the question. Fugacity. Can you tell me? Just tell me. By the way, when this happens, sir, accept, sir. Accept. Fugacity. What is the ideal pressure? Tell me though. What is the P ideal in this case? I'll ask you some questions. P ideal is what? Can you tell me easily? Easily tell me. This is the situation. Two things in given means third is given. Through the relation, quick relation, F by P is P by P ideal. Good boy. If you do this, P ideal will be actually P square by F. Happy? If you do this, you will get a value I have calculated 105 atmosphere. P square. Okay. So that tell me G of this is a P ideal. This is actually so. Under this condition, there will be ideal pressure. What is ideal pressure? Ideal pressure, sir? This is say 95 atmosphere has the same free energy. I'm coming to 95 atmosphere ideal is this is over. This is they are over. You can draw a line there. I'm just prolonging this discussion, and I am saying that what is the value? I already told you that this is geometric, etc. The three things you have got this problem, and you are in a kind of satisfied. But question is what? So G of 105 atmosphere ideal nitrogen against pitted against G, ideal nitrogen. What is the ideal pressure? What does it mean? What I said? If nitrogen were ideal, then this would be the Ideal pressure. Three things. This is the fugacity. This is the real pressure measured from the barometer. This is the ideal pressure. Means what? What do you mean by? If it followed the equation PV is RT, then this would be the pressure. But it does not. It is real. Real. That's what pressure it exerts. What pressure it exerts? 100 atmosphere. Okay. See. This is real less than ideal. Fugacity less than real. F by P is P by ideal. This is less than this. This is less than that. Obviously, makes sense. What's it? P, F is less than P. So is similarly P is less than P ideal. So, P ideal is the greatest. So in a sense, right? You write that also. Enjoy. So here you write comment F less than P in this case. Happy? A less than P ideal. For ideal gas, what is this? For ideal gas, A is P ideal. Okay, also over. So last is a additional question. This I have drawn the line. The answer is over. Three ways quickly. Which is are the same. This is ideal nitrogen. So nitrogen is an ideal gas. This energy same. Greater, less. It's a separate question. Total separate question. Since free energy is important issue, we have get this. So this ideal, so ideal I've taken up. But suppose 100 atmosphere is also ideal. 90 ideal, 100 atmosphere ideal. I'm 105, 100 atmosphere. Which is that's it. Pressure increases. What happens to free energy? So ask VDP, sir. Ask VDP, sir. Obviously, pressure increases, free energy increases. Obviously, get us, sir. So have feeling of these variables. Okay, what it does. Written the equation. Oh, it increases. Oh, it decreases. So, okay, over. Huh? Achha. Can I just complete Joule-Thompson effect? Just this one, Joule-Thompson effect. Huh? Joule-Thompson effect. Okay, this part, this discussion was pending. Now I freely move on. Achha. It depends upon how smart you are to follow this. But I will Joule-Thompson effect. I tell you as a prelude. See, when a gas is when a real gas like nitrogen, or carbon dioxide, I am giving another name, carbon dioxide, not hydrogen, like nitrogen, carbon dioxide is okay, is actually is okay, is passed through a porous plug. Porous plug through a porous plug, or you can call this key. What is this called? Because okay, pass through a, or what is it called? Throttle valve or throttle valve. These are technical names. Throttle. You have read this. I tell you. I will correlate. You have fluid flow problem. So throttle valve pass through and a significant pressure drop occurs. Accompanied by drop in temperature. That's cooling. Drop in temperature. Hence the name cooling. Joule-Thompson effect means Joule-Thompson cooling here, and if you put hydrogen, same experiment, will be heating. Okay. So this is I actually show you what is the polar. This is the throttle valve. I show you here. This is the throttle valve. You have gone through this. Flow, fluid flow, gas inlet, gas outlet, nitrogen. What will happen? Throttle valve, why, sir? No, why, sir? Not regular, sir. Uniform diameter. Pressure drop, friction factor. Fluid flow, pressure drop. For there are various reasons for pressure. One is length itself. Another very significant, very effective, diameter. Decrease the diameter. This is another thing. This is a friction factor, pressure drop. Okay. For the same flow, there is a greater pressure drop. Okay. Gas inlet. So that will be throttle valve. This is also needle valve. I tell you, you can see needle valve also. Throttle valve. I'm writing for you. Throttle This is the technical term very popularly used with the Joule-Thompson effect. Also needle valve. Why I am telling needle valve? I will tell you one thing. If you go to your lab, extractive metallurgy lab, sooner or later, you will see there is a cylinder stuck up there, okay, stacked up there, carbon dioxide cylinder. Ask Jayanto Babu, sir, please turn on the cylinder, the valve, turn on the valve. Valve is a needle valve, gas, high pressure, carbon dioxide comes out through a small diameter needle valve. Tremendous pressure drop coming. That you just extend your hand and see it is cold gas coming. It can be so cold at times when pressure drop is actually more significant. It can be so cold it will be ice, dry ice, carbon dioxide. There is no conversion to liquid state, directly solid. This can be shown in phase equilibrium chapter. I'll discuss this. And this happened in one case in one on my brother actually. He was narrating this thing. This happened. The gas actually by accident. The gas came out and there's an actual tree up there, and they are the leaves. This tree actually, these branches and all these leaves and all these things, they are actually covered with ice, a coating of ice of carbon dioxide. Why this happened? Joule-Thompson. Tremendous. More Joule-Thompson when you come across, tell me, guess. Ammonia, I remove ammonia, then
Methane.
carbon dioxide, methane. Ammonia, methane, maximum lower ammonia. And this also, there are many consequences. Easy to liquefy. This easy to liquefy also. Now, compressibility is what? Oh, compressibility what? Tell me, there. Compared to ideal gas, less. Less means easy to compress. So methane is easy. Ammonia easy to. You high school also said easy to liquefy. Yeah, sir. Less than one. Hydrogen is not. So liquid nitrogen, you will see, you can buy liquid nitrogen. Temperature is actually say 77 Kelvin. You buy at a lower price than liquid hydrogen. Hydrogen is very difficult. Hydrogen under heating normally, but you actually consider such temperature, there is inversion of Joule-Thompson effect. Then it is cooling, so that's why it is very difficult. Liquid hydrogen, even still lower temperature. So these are the consequences of fallout of this discussion. Okay, so see my point. So this is actually, so anyway, we consider cooling part. Throttle valve or porous plug. Porous plug written. Porous plug. Porous plug in refractory. You go to the extractive material laboratory. Refractory, you go. Furnace means refractory. Refractory means there are pores, fine pores. You pass the gas through this. This is it will come out, but a tremendous drop. It's very high drop. So that is the atmosphere. Outside the atmosphere. So high pressure, you have to force the gas. So tremendous, so that there is a cooling factor. So porous plug or throttle valve. Okay, this is the situation. This I'll explain. What else are going to? So liquefaction is another fallout. Liquefaction is another fallout. Is what I see. So what you said, cooling. But cooling is such that it will be. You can have actually cooling means liquid formation. Liquid nitrogen means cooling such that it will be liquid nitrogen. So these are the things I didn't write here, but you understand. I am giving you Joule-Thompson lecture. Follow me. Please follow this figure. This is my porous plug. See my point? This is my porous plug. Very interesting experiment. This is my porous plug. This is porous plug. Quickly, finish this quickly. Here's time. What I am doing here, I have actually this side. This is whole thermally insulated. Means adiabatic condition. I am concerned. Thermally insulated. What is the experiment? Joule-Thompson experiment. I am doing Joule-Thompson experiment. I am showing you. Simple sketch. First, see, there is a piston this side. Cylinder piston arrangement. Okay. This is a cylinder I have drawn. This is a piston. Give me the piston is where? Where is your piston? Good boy. Okay. This is the suppose. This is the volume. Okay. Okay. I'm very sorry. Don't mind. Remove this, please. Here. Bring it here. I have an advantage. This is your Saying that this is the initial state. What pressure it is? P1. What is the gas here? Gas. What pressure? Tell me. Gas. What volume? What pressure? P1. V1. This side also similar thing is there, but this side is what happens. I tell you. There is also. This gentleman is also P1. This side, that side, across. This one side, other. One side gas volume V1. Volume here what? This is the volume. Yes. Volume V1 means this much volume. Okay, so shall I show here? Unnecessarily I will not increase arrows. This is the volume. Gas is what is the temp? There is a certain temperature T1 I have given. Temperature is T1. Okay, temperature T1 I will write T1. Okay, I will write this. Temperature T1. Pressure P1. Okay, good boy. This is okay though. This is there. This side is what is this? This is fast with the brick or porous plug. This is fast. Yeah, here it is there. This fast with the wall. Fast means no volume. This side no volume. This side volume is V1 gas. I will squeeze this gas through the other chamber. So P1. So there is no gas equilibrium. So porous plug I have written here. Porous plug. Okay, sorry. Porous plug. It's okay. It makes sense. So what is this? At equilibrium. State 1, right? State 1. You are interested in state 1. At equilibrium, what are the configurations? Please tell me. State properties. Please tell me. Pressure is 31. Temperature is 30. Volume is V1. Temperature T1. And if you are interested in internal energy E1, enthalpy H1. This is the status. Figure 1. Okay. State 1. This is the state 1. I'm right. State 1. I do what I before I draw. I tell you. I will suddenly make it P2. Equilibrium, I disturb the equilibrium for something to happen. So that something. So note here, P1 is actually much greater than P2 is less than P1. I made this. Then what will happen? This will force the gas through this, and this will squeeze the entire gas, and this will come out this side. Entire gas squeeze. Then what will be figure like? Draw again. Similar exaggerate. Draw 1 to 1. After this compression has the expansion, what will happen? This cylinder, see, squeezing the gas, squeezing gas. This will go this. So this is porous plug. Okay, place the porous plug. Porous plug. This is porous plug. Pores. Blotting paper is an example. Blotting paper. Pores are there. Fine pores means difficult to pass the gas. Happy? Porous plug. So what is the status? Where I draw this? Who is this? Tell me. Tell me, this is part of 1. This is plus to this. I'm drawing actually plus. Here it is plus. What is this pressure? What has been this? P1. P1. That's why it is P1. And what is the other side is what? Tell me. This will the volume will be what? Expanded cylinder is there. This will be gas cylinder piston expanded to. This is V1 volume greater than that. Lower pressure greater. So maybe little bigger. Good enough. So you have this side piston. Okay, this is the volume gas. Right hand side gas volume V2. Okay, P2. What is the pressure here? This side you have made it. Tell me. P2. Remember I told you. You might say, sir, this is P1. This equilibrium. Step 2. Step 2, right? Step 2. At equilibrium, what are the configurations? Tell me again. The pressure is this side, this gas. P2, volume is V2, temperature is T2. Right? I am writing before to you. T1 is greater than T2. T1 also greater than T2. T1 is greater than T2. Means T2 is less than. Okay? This I will show you. This I will tell you. Okay? P2, what is U2? H2. Follow me, please follow me. Interesting coming, okay? So see, P1, P2, you might argue, sir, this side difference equilibrium. Are against this room maybe high temperature, that room is a wall, insulating wall. You can. Moreover, who is here? No one. Pressure high, so what? This is meaningless. Okay? This is actually no gas actually. So only it is zero. There is no gas. So this is P2. But this side you consider. This side you consider. This side you consider. After quizzing, before quizzing. So this is now quickly. First law. I show you something. We are at the first law. It's okay. Does it? Does it? Letter I can write at the top now very easily. Okay. No more recording.
It is recording, but here is light. There is some amount of light on that
Light?
light means near the door. That light the rule is reflecting and that's reflecting and that
So now only all through.
not all through, sir. Now I think it is more prominent.
So I had turn this light off. This light
No. So the board has
or that one.
yes. But the board has mandated.
Maybe. Maybe because schedule me just that actually. অসুবিধা ওটা it's okay. State 2, so this is gas is squeezed and this has flashed. Mark the word flashed. It has flashed with the wall, and this is actually then it was flashed previously. Now it has taken this position. Volume of V2. So volume of V2. This is volume of V2. This is the now this fully gas is actually squeezed past, squeezed through the porous plug. So no gas is left this side. So and is actually greater volume. So V2 greater than V1. You may write. So what happens? First law. I'm writing here. So continue from this point. Quickly. First law application applied. Q is very interesting application. Today you have not used these two compartments. You have never used. One gas cylinder. Here two gas cylinder. Two cylinder piston. One cylinder piston you are used to. Q is what? This thermally insulated. I write this. Right here also. Thermally. Don't ever forget this. Thermally insulated. Oh, I have to write bigger font now. Thermally, sorry, I'll maintain that. Thermally insulated, and this you write here porous plug. You write this porous plug. You will check porous plug is seen.
Yes, it is.
Porous plug is okay, though. Okay. Now sit down. This is the limit. Now start it. Start from this point. So explanation. First law is Q. Quickly. What is the value of Q? Q is what? Follow. Adiabatic. Thermally insulated. No heat comes to surrounding, so 0. Delta U is what, sir? State 2 minus state 1. Have I written here? Yes, U2 minus U1. W is the challenge. W is challenge. Follow. One side gas is compressing the gas, and another side this is expanded. So this side will be all done on the system. On the system, this will be by the system. Then the gas will by the system is positive. So that we write first. What is the by the system? Please tell me. Yes, they open ball. See, it was P2. Now P2 with this load, it is expanded. So work is PDV type. Okay, P2 and constantly sitting P2. So P2 times volume change. What is the volume change, sir? V2. Great. Is okay. Can I proceed?
Yes.
P2 V2. The one side P2 V2, but minus P1 V1. It is the work that says this load is squeezing the gas. On the gas is a system. Minus P1 V1. Happy? Or quickly is U2 plus P2 V2 minus U1 plus P1 V1 is known as H2 minus H1. Enthalpy is what? This. That is delta H is 0. So it is an isoenthalpic process. Okay. How will I remove this? You don't need at all. You don't need at all. How do quantify Joule-Thompson coefficient? So now Joule-Thompson coefficient you can do yourself. So what happened? Why T2 is less than T1? I wrote here. Since it is still there, P2 is less than P1. Hence T2 is also less than, means there is cooling. As it overcomes this barrier, so there is cooling. So when your Joule-Thompson coefficient is given as mu. Mu is what? Del T how temperature changes, how much cooling takes place for for unit change in pressure, okay, for how much pressure, etc. So del T, rate of change of temperature is pressure under constant enthalpy. This is the Joule-Thompson coefficient. This is remarkable. Is what? And you are smart here. You are very smart here. What you will? This is very constant enthalpy. Don't touch. You ask me comment. Very difficult. Also, we do not know, sir. We CPs the constant pressure, constant volume, you understand. Enthalpy, oh. So what will you get rid of this? How? Transformation formula. And see, magic. What is this? Del H by del P. Tell me, you are master in this, I hope. Del H by del P at constant temperature divided del H del T. Very good. Now tell me, keep on telling, keep on proceeding yourself. Enjoyable, sir. Del H, what is this value? Yes, Anurag. Del H by del P at constant temperature is what? See, what is the system? You see, on gas, nitrogen gas. I want B into 1 minus alpha. You remember, Nijor? What is the effect of, what is this value? Del H by del P at constant temperature, remember? B times 1 minus B is molar volume, you remove 1 more. And what is del H by del T at constant pressure? Nijor, what is del H by del T at constant pressure? Is the easiest of all. Heat capacity. Don't forget, thermodynamics is valuable for whole life. Because don't forget, don't consider your this B, any. So once you demand, okay, sorry, I start talking. CP, okay, shall I write this? Mu is, will you give a box? And that's it. Now you understand. Quickly, tell me, what is for ideal gas? Corollary, quickly, corollary. We are all set. Since you are giving me so much time, so let me complete this. Corollary, quick, for ideal gas. Hey, you see though, well, you check. Okay, keep on checking. For ideal gas, I'll be very happy. For ideal gas, mu is what? I'll be very happy if you can answer this. Alpha. Take a look at the alpha. 0, 1 by T. Write this for ideal gas. Alpha is 1 by T. Right? That is a property. Good, very good, very good. You retain something. That actually gives me some satisfaction. So the V is alpha T. So mu is 0. So no Joule-Thompson coefficient. No Joule-Thompson cooling, heating, etc. Nothing. Ideal gas. Because the reason is, I tell you, I can remove this. The reason is that there is no attraction or repulsion between molecules. So this is the for nitrogen. Tell me for nitrogen. I tell you, for nitrogen, what is the mu key hobe? Mu. If you do this, actually, substitute mu will be positive. Positive means this will positive. What does it mean? If you always your pressure is falling, pressure is from one side to another, pressure falls, so temperature will fall, means cooling. So this what means Joule-Thompson cooling takes place, which you often call Joule-Thompson cooling, you say. And for nitrogen or carbon dioxide, no, or carbon dioxide, right? This some other gas also, right? For hydrogen, what you have mu is negative, because means when you are passing the gas from high pressure to low pressure, there is actually heating. So this is Joule-Thompson heating. So this is actually our study. Now I quickly summarize, just 3 minutes or 4 minutes. The difference between Joule-Thompson cooling and adiabatic cooling. This is very, you will answer. This will question and answer section. Not actually because adiabatic, So very important. Shall I write here? Can I write? Shall I write here? So compare Joule-Thompson cooling and Joule-Thompson cooling and adiabatic cooling. Cooling I am giving, sir. Heating I am not considering, both adiabatic cooling. You recall what is adiabatic cooling? I am giving. You remember expansion of gas? 1. 4 points or 3 or 4 points. Okay. What is this? For ideal gas. Tell me. JT Joule-Thompson cooling is. Tell me. Is what? How much? 0. Right. For ideal gas, there is adiabatic cooling. Is it 0? Then we have not started adiabatic process. What system we use in the all this adiabatic